Start webinar.
We're still in
Okay, stand by.
Start webinar.
Welcome to Wicked Problems, Wolfpack Solutions. Tonight is the first live stream event in the series, and this will be the only event in which there are, in fact, no problems, though we will be talking about the end of the universe. My name is Matt Shipman. I'm the Research Communications Lead at NC State University, and this evening I'll be talking with Dr. Katie Mack. Katie is an assistant professor of physics at NC State and the author of a fantastic book called The End of Everything. She is an expert on the universe. So we're going to be covering a few billion years worth of material here. So I'm going to go ahead and get started. Katie, you're a cosmologist.
Mm-hmm.
What is a cosmologist?
Well, so first of all, thanks for the introduction. I'm really happy to be here to be talking to everybody. A cosmologist is somebody who studies the universe from beginning to end, from the largest scales to the smallest scales, what the universe is made of, how it works, all of those aspects of the sort of function and evolution and origins and fate of the cosmos.
Okay, so like one of the things that I think a lot of people, it's not something that they know about cosmology, but it's something that they think they know about cosmology. Is the Big Bang Theory. But our understanding of the Big Bang has actually evolved quite a bit over the past 50 years or so. So how would you describe our current understanding of the Big Bang?
Yeah, the Big Bang Theory is I think one of the most talked about things in cosmology. One of the things that you talk about the Big Bang and people on the street are like, yeah, I know about the Big Bang. But when it was first sort of brought to the public eye, maybe in the sort of 70s or 80s, it was very different from how we talk about the origin of the universe today. So people usually think of the Big Bang as a singularity, an infinitesimally small point, and then some kind of explosion into space, or and then that creates the universe. And we actually don't have any reason to believe there was ever a singularity. There was ever a sort of infinitely dense point at the beginning of time. That idea comes from taking the fact that the universe is now large and it's expanding, and dialing that back and using our theory of gravity, general relativity, Einstein's theory, and just extrapolating back. And if you do that, the equations lead to this infinitely dense point. But we actually have really good reason to believe that that is not how it went. It didn't go from just tiny point and then explosion, expansion straight from there. When we talk about the Big Bang Theory as cosmologists, we are talking about the idea that in the past, the universe was hotter and denser and in some sense smaller than it is today. And we do get that just from extrapolating backwards, saying the universe is currently expanding. It must have been smaller and hotter and denser in the past. And we have really direct evidence of that, which is very cool, which I'll talk about in just a moment. But the idea that it goes all the way back to a singularity, actually, we based on our observations, something must have happened in between. If there was a singularity at all, then something must have happened between that and what we see today to explain what we see in the universe. But we are very, very sure that the universe was hot and dense in the past. So hot and dense that all of space was full of like fiery plasma. And the reason we know that is because we can actually see it. Because if we look out into the universe far enough away, we are seeing light that has taken so long to reach us. It's taken, the age of the universe, 13.8 billion years to reach us. And that means that light has been traveling since the time the universe was just beginning, since the time the universe was hot and dense and in this sort of fireball state. And so that means we can actually see the fire. We see the
Right.
Big Bang. We see the light from the Big Bang. We call that the cosmic microwave background because it comes to us as microwave radiation, which is just a kind of light, a kind of electromagnetic radiation. But we see that light very directly, and so we can actually see the universe in its primordial fiery state in the process of the Big Bang.
And so this cosmic background radiation, the sort of like light echo of the creation of the universe, what can we extrapolate from that? What can we learn from that?
Yeah, so the biggest thing we learn is that the universe was, was hot and dense and glowing with heat in its first 13.8 or its first 380,000 years in the very beginning. The other thing we can do with that light is we can look at the little fluctuations in that light. So there are some, when we look at this, we're sort of looking out at the farthest reaches of the universe. The most distant thing we can see is that background light. And in some places it's a little bit hotter, and some places a little bit cooler. And that's because when the universe was this sort of hot, dense, fiery universe, it was sort of churning and humming and vibrating. And there were places where it was a little bit hotter and denser, and places where it was a little bit cooler. And so there was it was a little bit bumpy, right?
Right. So it wasn't totally homogeneous.
It wasn't totally homogeneous. It actually had sound waves going through it. We can see the imprint of those sound waves, which is very cool. But what we can observe is that the places where it was a little bit more dense, over time, those would grow into clusters of galaxies, the largest structures we know of, and places where it was a little bit less dense, that grows into voids, giant empty spaces in the universe. And by looking at those patterns and seeing, what happens to the light as it passes through all the rest of the universe, we learn about what the universe is made of. We learn about the components of the universe. We learn about the evolution of the cosmos, how the expansion has been happening since that early time up to today. And we can even get sort of hints about how the universe is going to go in the future, how it'll end, based on what we learn by looking at that background light from the very early stages.
Right. But that's one source of pretty amazing source of information or observation that we can use to understand things. What are some of the other sort of phenomena or tools that we can use to understand things at the universal level?
Yeah, so in cosmology, most of what we're doing is we're looking out into the distance in order to look into the past, right? Because the farther away we look, the farther back in time we're looking. And so we can use any distant objects to learn about the history of the universe. We can look at distant galaxies, distant clusters of galaxies, supernovae that went off in distant galaxies. And so as we look at these other galaxies, we're seeing the light as it was when it left those galaxies, when the universe was much younger, much smaller. And so we can count up how many galaxies there were, how close they were together, when they formed, just by looking at really, really distant objects. So it's kind of like we have this timeline going out from the present now here to the past very far away, and we can look at everything along that timeline, and that's just the distance. It's a space line, but it's also a timeline because of this speed of light. And we have that in every direction. Every direction we look, we can stretch out a ruler in terms of how far away we're looking, and see the past in every direction. And so we can fill in this really amazing map of not only the space of the universe, but also the time of the universe, the past, the history of the universe.
So the various telescope type tools that we have are effectively windows in time.
Oh yeah, absolutely. I mean, like the Hubble Space Telescope can see galaxies that existed within the first 500 million years of the universe. The universe is 13.8 billion years old. So, the first 500 million years, first half a billion years, that's a long time ago. That's very, very early stuff. And we're getting new telescopes soon that the James Webb Space Telescope, the sort of successor of Hubble, that's going to see even, maybe some of the earliest galaxies that ever formed in the universe, and it's going to tell us about how galaxy formation even happens, what galaxies were made of at that time, and how the first stars came together, and so on.
So, sorry, this is a lot.
Yeah.
So based on all of this data that we've been collecting, that humans have been collecting through looking at the sky, and then with much more modern tools within the past century, based on all this information that we have, what needed to happen for the conditions to exist for there to be life, right? Like anywhere, not just us, but just like life at all.
Yeah, that's a great question. I mean, in terms of the conditions for life on sort of a single planet, there are things we think we know, based on sort of extrapolating from Earth life. We know that Earth life needs water, it needs a source of energy like the sun, or maybe potentially a hydrothermal vent or something like that. And it needs certain sort of molecules like amino acids, things like that. And we know that those conditions do exist fairly frequently in the universe. So we think it's probably true that there's life in a lot of places in the universe now. Whether or not there has been life, all along the timeline, that's a different question. And we can definitely see that there were times in the distant, in the past in the universe where there just couldn't have been any kind of life that we know about, when the universe was in this sort of fiery state at the beginning, when the whole cosmos was full of this sort of humming plasma. We don't think there's anything that could have lived in that. It's just way too hot. And then, then after that, that fire cooled, then the universe was mostly this kind of neutral hydrogen gas. And then that came together to form the first stars and the first galaxies. And so when the first stars and galaxies formed, that sort of set up the conditions for the structure that life needs, something to live on, something to derive energy from.
Right.
But we don't think that'll continue into the indefinite future, because as the universe is evolving and changing, the way it's evolving and changing is that things are getting farther apart. Matter is getting more diffuse. Energy is getting more diffuse. So the universe is expanding. And I said that a couple of times. What I mean by that is that we see that galaxies are getting farther apart from each other. Distant galaxies are getting farther apart from each other. So there's kind of more empty space all the time in between things.
Right.
And one of the things that does is it makes it less common for galaxies to collide with each other and bring new gas in to create new stars, because galaxy collisions are one of the ways that big bursts of star formation happens. And as galaxies evolve, as time goes on, the hydrogen gas that's inside those galaxies gets turned into stars, and then those stars sort of burn out or explode or whatever. And so galaxies can kind of use up their gas. And so over time, it's harder and harder to make new stars, and harder, therefore, to make new planets. And then, that makes it less hospitable to life. And so we can actually see, based on our observations of the distant past, that star formation was much more common early on in the universe. Maybe in the first like half a dozen billion years there, or even earlier than that. The first few billion years, star formation was really common. There was a lot of hydrogen gas. There were a lot of galaxies colliding with each other. There was big bursts of star formation, and it's been slowing down since then, since the first few billion years.
Has it slowed down so like we're in the sweet spot, or are we sort of after the sweet spot?
You can calculate how many stars have formed so far in the universe and how many we expect to form in the future, right? And about how far in do you think we are? It's not 50%.
70%?
90 or 95.
Wow.
Yeah.
Cool.
Yeah. So like 90 or 95% of all the stars that ever were or ever will be have already formed. So we're in the kind of winding down middle age, kind of like senior citizen part of the universe right now.
The early
like
bird
the conditions,
special era of the universe.
Yeah. I mean, the conditions are pretty good for life right now. You might even think you don't want to live when the stars were at their peak formation time because there were lots of supernovae going off all the time, and you don't want to be near a supernova when that happens, right?
Right.
So and when there's lots of galaxies colliding, you get more galactic activity, you get, sort of bursts, jets of radiation. That's not great. So maybe it's better to live kind of in this sort of latter times when everything's kind of calming down and you have a bunch of sort of middle-aged stars and their middle-aged planets. But yeah, I mean, if you fast forward 100 billion years in the future, the stars are basically done by then. There are very few stars that live much longer than that, and it'll be a lot harder to have any kind of new life forming then. So we are kind of in this period of time in the universe where stuff can happen and we can discover things, but that doesn't last forever.
Okay, so very quickly before I forget, I just want to, so some of our viewers are NC State students, many of them, and we also have viewers who are watching on YouTube Live from wherever in the universe. Hello, viewers. But the NC State students can ask us questions, and we encourage you to do so. I know we've already got a few coming in. We're going to get to those in just a second. I had one more question I wanted to make sure that I asked. I'm not going to ask about all the ways that the universe might end, because Dr. Mack wrote an entire book about it, and we don't have that kind of time on our hands to go through a book's worth of stuff. But a lot of people, how do I phrase this? So one of the things that I think is pretty common is a lot of people think about just the concept of the universe ending and find it totally overwhelming, right? So,
Yeah.
or depressing or sad or whatever.
Yeah.
But I've read the book and I know that you don't feel that way. So like, what perspective do you have on the end of everything?
Yeah, I mean, this is something that I kind of struggled through in the writing of the book, like trying to find a way to relate to that idea, and not have it just be sad, right?
Right.
And in the process of writing the book, I went and talked to a lot of my colleagues, a lot of cosmologists and physicists, and some of the most eminent people in the field, and I asked everybody, questions about their research, questions about the fate of the cosmos, the latest science, the new observations that are coming up, what they're excited about, all that. But I also made sure that every time I went for one of these interviews, I also made sure to ask, how does the end of the universe make you feel?
Right.
And I wanted to know, like, how they sort of emotionally internalize this stuff as they're working every day on, the fate of the cosmos. And there was a huge range of responses. Some people, a couple of people said they thought it sounded really depressing, that the universe sort of fades out and everything gets cold and dark and whatever. A few people were like, yeah, it's fine. That's how it should be. We should just be a kind of little blip. It's all good. One person said, I don't think anything about the end of the universe. Like, I'll be happy if we figure out what to do about climate change. I don't mind what's going to happen in 100 billion trillion years, whatever.
Right.
But I think for me, what it came down to was just a different sort of perspective on the cosmos, and a different perspective on like where we fit into this big story. The cosmos, the universe has its own story. It has a beginning, a middle, and an end. And we are fortunate enough to be able to learn about that, to be able to observe pieces of that story, to figure out how it all fits together. And we can find kind of our own place in that. And, maybe there's no great meaning to the universe, depending on how what your beliefs might be. There may or may not be an essential purpose to the cosmos, if it's going to end and everything's just going to fade away. And, maybe like you might think, well, maybe nothing matters. But I think for me, what I get out of that is that we need to find the meaning in the cosmos, or in our lives, in what we're doing now. And that meaning that we create, that meaning that we discover, that's important. And we can see ourselves fitting into this bigger picture fitting into this larger story and find meaning in just in that, in being part of that larger perspective.
Right. I mean, if everything is finite, like everything is finite, then that makes everything that much more precious, really.
Yeah, yeah, absolutely.
Yeah. So, so advancing our understanding of the universe is, I think, inherently interesting, right? Like I at least find it incredibly interesting.
Yeah.
Does it have like a practical utility at all? Like, is there?
So the short answer is we have no idea, right? When theoretical physicists of the past were working on esoteric things that were, big important questions, many times those things turned out to be immensely practical in ways that nobody could have predicted, right? When people were working on electricity, I mean, nobody knew that was going to be useful when it was first discovered. When people were working on quantum mechanics, nobody knew that would be, underlying everything that happens inside of your cell phone, and would allow us to do all this amazing technology. When people, when Einstein came up with general relativity, this idea that space-time bends around massive objects in space and it changes how time flows, nobody thought that would have any practical usage. But now, if you use a GPS thing in your phone, you're using general relativity every day. So it's very possible that by asking these big esoteric questions, by really trying to push the boundaries of our knowledge of physics and the universe and how it works, we will find something that will have a practical use in the future, and we'll have no way of predicting what that will be. And we've found time and time again that there's just a huge return on investment of doing basic research, especially in something like fundamental physics. But I think, so there's a sort of economic or practical argument for it. Right. But I think for me, the reason that we should do this kind of science is because, like, humans want to know stuff. Like that's part of what makes us humans, right? Like, we are curious, and right. we want to understand the world around us, and it's that instinct, I guess, has served us well over the millennia that we've been around or whatever. But it's part of our basic humanity that we want to know the answers to these big questions. And so I think that there is a basic good in, like, indulging that human instinct and trying to increase our knowledge and increase everyone's access to that knowledge. I think that's just a basic human good.
Okay, so so this sort of, I think, segues pretty well. One of the students, Ryan, would like to know what it's like trying to solve the mysteries of the universe. And are there some things that are just unsolvable? Are there some things that we just can't know?
Yeah, so I think that there probably are some things that we will never know. I mean, we will not personally see the end of the universe, so we will not know exactly how that's going to go, right?
Not for
there
long,
also,
anyway.
Sorry?
Not for long, anyway.
Yeah. And there are also there are also some basic limits to our knowledge that are built into how physics works, as far as we understand. Like, there's a limit to what we can know about the smallest scales, because things get very sort of wiggly on the in a quantum mechanical way, uncertain on very small scales. There's also a limit on the largest scales, where there's a limit to how far we can see in the cosmos, how far we can get information from, because of how long it takes light to travel from the most distant reaches. So there are some hard limits to what we can know. But for me, like, I find it very rewarding to work on questions like this, because, maybe we can learn a little bit, maybe we can get a little bit closer to something that might give us some insight into the way the universe works. And even if my part is just an infinitesimally tiny piece of a bigger picture, it's nice to feel like I'm sort of contributing to that. And it's just fun to play around with these big, ideas. I really enjoy that. And especially the part of physics that I work in, is a part where I get to be really creative, where I get to basically I talk to the theorists and I find out what are the big and interesting theories going on right now, and then I talk to the observers and I find out what are the telescopes you're going to build, or I talk to the experimental physicists and ask about the new like colliders or whatever, and I try and find ways to connect those things and say, well, if you're doing this observation, you might be able to learn about this model of how dark matter works, and then that can tell us something really cool. So that's I just enjoy that a lot.
So you mentioned dark matter. Another one of the student questions from Zach had to do with dark energy and dark matter. So for our viewers, what are dark energy and dark matter? And then Zach wanted to know how those things influence the universe.
Yeah, so dark matter is, as far as we know, it's a kind of matter. So matter is something that has mass. It's it has gravity. So dark matter seems to be a kind of matter that just is invisible. It doesn't interact with light, as far as we know, and so we can't see it, but we can see how it acts on other things in the universe. We can see that, for example, stars that go around galaxies stars are sort of orbiting galaxies in these disky galaxy shapes, right? We can see that some of those are moving faster than we would expect if only the matter we see is what's there. So that leads us to believe there's more matter there that's holding those stars in. And there are lots of ways you could interpret that particular observation and get to places other than extra matter, but we have other really compelling pieces of evidence that there is just this extra matter in the universe that we can't see, which is not that unusual. There are other kinds of particles that we can't see that don't interact with light but interact other ways. So it's some kind of new particle we don't know about yet that has this property, probably. We don't know for sure. But that's dark matter. So dark matter it's most of the matter in the universe, right? So it's like 80% or 85% of the matter in the universe. So it's a lot of the stuff that's out there. Galaxies are mostly dark matter, just a sprinkling of stars. Whereas dark energy is kind of the opposite thing. Dark energy it's also invisible. That's why we call them both dark, because we can't see them. But dark energy is something that's making the universe expand faster. So I mentioned the universe is expanding. It's actually speeding up in its expansion. And we don't know why, but whatever is making it speed up in its expansion, we call that dark energy.
So it's what's pushing the universe outward?
Yeah, sort of. It's pushing things away from each other. It's just accelerating this expansion that was already happening from the Big Bang. So it was the Big Bang caused the expansion to start. It started expanding, and then it was slowing down because all the gravity of all the stuff in the universe was pulling together, kind of putting the brakes on the expansion. And then, something like 5 or 6 billion years ago, it started speeding up again. And that speeding up is due to something, and we call that something dark energy. And we don't know that much about it. So, we don't know why it sort of is doing what it's doing. We think that probably it's something that was always part of the universe, always part of how the universe worked. And the reason it just started making the universe expand faster in the last sort of 5 or 6 billion years is because the universe got big enough that the gravity that was slowing everything down was weaker because everything was farther apart. And so then this pushing kind of took over.
That's really cool. Okay, so this next question I also think is super cool. This one's from Catherine. She wants to know if we've found evidence of life outside of Earth. And if we haven't found evidence of life yet, do we have likely suspects, like places where we think we would be more likely to find life?
Right. Yeah. So we have not found anything that I think the scientific community would agree is a sign of life elsewhere. I'm putting a lot of caveats on that because there have been little detections of things various times where people have been like, oh, maybe that could be a biosignature or whatever, but nobody's said, okay, definitely this is it. Or at least, we haven't agreed on definitely this is it.
Right.
But there are some places that we do think are good to look, right? So there's Mars is one place where we're definitely looking. We're looking partially for past life because we know that the conditions on Mars in its early millennia, early on in Mars's history, a billion years ago or something, it had conditions that were much more favorable to life as far as we know. It had liquid water on the surface, had a thicker atmosphere, it was warmer. So there was liquid water on the surface of Mars in the past, and we think liquid water is something that is conducive to life. So maybe there was life on Mars, and so we're definitely looking for it. Like the Perseverance rover that's there now is designed to look for signs of past life or present life even, although that's the harder to see how it would still be there.
Right.
And then there are also a couple other places in the solar system where we know there's liquid water in weird ways. So some of the moons of the gas giants, Saturn and Jupiter, have water under their surfaces. So they have like maybe an icy surface that's a few kilometers thick, and then there's a liquid water ocean under that. So there are a few of those little moons that have a setup sort of like that, and maybe even like hydrothermal vents underneath,
Right.
where life could totally take hold if the conditions are right, if the right molecules are there. So
And are these like the actual small moons? I know some of the moons around the gas giants are actually ginormous.
no, so these are I don't know. I think these are sort of like medium to large ones. They're not like the tiny little rocks that are in Saturn's rings or anything like that.
Yeah.
But they're big enough that they can have a sort of ocean inside them. But I mean things like Europa and Ganymede and or Enceladus, and Saturn's moon Titan, which is also really cool because it has a liquid ocean of hydrocarbons on the surface. And then it has liquid water under the surface also, which is kind of amazing. But yeah, and then we're also looking at planets that orbit other stars, so exoplanets, where we know that some of those are, sort of the right size for, similar size to the rocky planets of our solar system, and orbiting their star from the right distance so that maybe they could have liquid water on their surfaces. We're not really sure because we can't tell from here, but those are things that we're investigating more as well.
Okay. So this is sort of related, I guess. But Rohan asked, so rather than finding life elsewhere in the universe, his question was more about how quickly we could take life into the universe. So like how viable do you think it is that humanity could develop the necessary technology and become a multiplanetary species?
I mean, I think that's a hard question. Right now, we have the capability to live in space. We have a space station, but it's constantly being restocked by Earth, and it's it's not far away. So we didn't have to travel very far to get there. It takes maybe 6 hours to get to the space station from Earth, depending on the orbits.
Right.
So. And we've taken people to the moon. They've spent a couple days there, and so it is possible to live for a short time in a lot of places, I think. And there's plans to go to Mars, and a lot of people talk about setting up settlements of some kind, or habitations on Mars. And I mean, I think at the moment we're in the situation where it's kind of like living in Antarctica. Like you can do it for a short time. You need to be resupplied by other places where life is more sort of tolerated than that place.
Right.
And I think we could make a rocket powerful enough to take people to Mars. We are pretty close, I think, to being able to land something safely on Mars that has people in it. But probably when you get there, you're going to be living underground in like a lava tube to protect from the radiation, and you're going to be in a pressurized habitat the whole time, and you're going to be living on food you brought with you, because we don't yet know how to grow food there. Maybe you can take water from the ice under the soil to replenish your water supplies.
Right.
And maybe you can get oxygen out of that too. There's an instrument on the Perseverance rover that's making oxygen out of the carbon dioxide in the air. But it's not like a long-term, living there situation. And maybe we'll get there. I mean, I think eventually we'll probably find ways to solve the kinds of problems to live there. But I don't know that it'll ever be practical in any way. It'll probably always be like a kind of weird thing that, explorers do, but it's not, I don't see us like having like a significant population on Mars anytime soon.
Sure. So that's all like sort of near solar system.
Yeah.
Stuff.
Beyond that.
So like, well let me
Yeah.
recouch this, right? Or reframe this, right? Because Rowan had a lot of questions. His question was really
Okay.
involved and it's all
Okay.
super interesting.
Mhm.
So if we're thinking about things in terms of interstellar travel, right? So I guess two different questions. One is like, is it even physically possible to create like, say, warp bubbles to travel in that way? And then the other one is, what about stellar engines, or engines that would allow you to cross space in a meaningful way?
So in terms of the warp stuff, as far as I know, there's no physically plausible way to do that. Like even just theoretically writing down the equations, it's very hard to get something that seems to theoretically work. And then it's like, well, okay, so you can do this if you learn how to bend space. We do not know how to do that. We don't have whatever kind of weird matter you might need to keep wormholes open or something like that. Like none of that stuff is available to us. And then in terms of engines, there have been some really cool developments in spacecraft engines in the last couple decades, I guess, ion drives and stuff like that. You might be able to get pretty fast, but for a trip like to another star, I mean, even to Alpha Centauri, that system, that's about 4.2 light years away or something like that. It would take, based on current technology, it would take somewhere between 10,000 and 100,000 years to get there. Which is, at that point you've got like ultra generation ships, right? Like it's not a trip that people just make. So we don't have that technology yet. Maybe we'll develop the kind of technology to go fast enough or continuously accelerate and somehow not get torn apart by like space dust. And then we can use relativity to make it within a lifetime. But by which I mean, if you get going fast enough, then the distances get shorter, basically, from your perspective. So you might be able to survive a longer trip if you're going fast enough, if you don't run into anything. But that's still pretty far beyond our current technology.
Right on. Okay. So Gabriel wanted to place everything that we've been talking about in context, basically, or she. Gabriel
Okay.
can go either way. So the question, and I think that this is really perfectly phrased, right? So I'll just read it verbatim. And that's, was there anything before the universe formed? This may be a weird way of saying it, but where is the universe? And I just love that question.
Yeah. So for slightly technical reasons, we have a lot of trouble tracing back to the ultimate origins of the universe. Okay, so this is the timeline as we think we know it right now. Going backward, the timeline is like there was this expansion. There was the hot dense state, this cosmic microwave background that we see now. Before that, we think that there was a period of very rapid expansion called inflation, where the universe sort of doubled in size over and over again, and just rapidly expanded. And then that expansion, that really rapid expansion, sort of when it ended, it dumped a whole bunch of energy into the universe, created the fireball cosmos that we see when we look at the cosmomicrowave background. But this inflation, if it happened, we have no idea what came before it. And there are theories, but it's really hard to kind of extrapolate back before that based on our current knowledge, based on our current observations, because it sort of hides whatever happened before. Because it's like there was sort of a universe, and because of the expansion, it zoomed in on a tiny, tiny part of that universe, and then that's our entire observable universe, right? And so it's very hard to learn about what else was there. And we know there was a huge amount of space out beyond our observable universe. Our observable universe is a sort of bubble around us that's only like 46 billion light years in radius. That's how far we can see. Yeah, yeah, only. That's how far we can see before we run into the fact that any light from beyond that bubble would take more than the age of the universe to get to us, because of the amount of space it has to traverse and the amount of time that it's had. And so, anyway, there was probably this inflation thing, but before that, we have very little idea of what happened. Maybe there was a singularity, maybe not. We don't know. Maybe we're part of some much larger space where there's like bubbles of universe coming out, where there's little inflation, and then inflation ends. You create a little pocket universe, and there's another one over there, and they're sort of constantly getting farther apart from each other. Maybe there are higher dimensions of space, and we have our 3 dimensions of space here, and then maybe there's some 4th dimension that goes at right angles to all of our dimensions, and there's more space beyond that, and there's like a whole other universe out there. Like we don't know. So what, it's a little bit hard. It's like we're in the middle of a forest, and we can see the trees within our sight line, right? And we just can't see beyond those. And we're in a bit of a situation like that with the universe, where we're in the middle of it, or we're inside the universe, and it's very hard to get the outside picture, if in terms of like a global picture or just perspective on what's beyond our observable universe, because we don't have any information. So we're making a lot of extrapolations. We're doing our best with our mathematical models and trying to find things that are consistent. But there's a limit to how much we can really know about anything beyond our observable universe, and we know that our observable universe is not the whole thing. Right. So there's a little bit of a frustrating thing happening there.
Well, I think it's for Gabriel, it might be excellent news, because it sounds like there's a real cracker of a problem for them to work on.
Sure. Yeah.
So Gabriel, good question. Now get to work. Dr. Mack, thank you so much for joining us this evening.
Thanks for having
Everybody
me.
who sent in questions, thank you so much. We had a lot of really good questions. Left a lot of them on the cutting room floor, and I apologize. The Wicked Problems, Wolfpack Solutions, this is only the first one. There are going to be quite a few more. Please come back. The others have actual problems that we can solve, as opposed to entropy, which is insoluble.
Yeah.
And thanks so much, everybody. It was wonderful having you with us this evening.
Thanks, everyone.